and welcome to one of the Tech Byte video by CMG. My name is Reza Malakuti, and in this video I would like to give you some guidelines about how we can successfully couple the GEM and LedaFlow via our coupling link tool. In the coupling process between GEM and LedaFlow, one of the key criteria that can help us to understand if the coupling process has been successful is the reasonable match between the estimated bottom hole pressure by each application. As you can see on this right hand plot, I would show the well bottom hole pressure against time in a typical coupling process that we have done. And as you can see, there is quite a reasonable match between the bottom hole pressure between both GEM and LedaFlow. In order to find out how we can achieve such a kind of match between the BHP of these two applications, it is important for us to understand first how the communication between the GEM and LedaFlow will be happening during that coupling process. At time zero in the coupling process, GEM will generate the IPR at that time, and LedaFlow will take that IPR 0, let's say, and marches to the time step 1. Then LedaFlow will generate the Q1, or let's say the converged flow rate, and will be passed this flow rate to GEM as an operational rate constraint for our wellbore in GEM model. GEM marches to time step 1 based on that rate constraint and generate the IPR number 1, which will be used for the next time step, and this process will be consequentially going to the end of the simulation. We can now understand the importance of the IPR in here now, because at one side, which is GEM, this IPR will show the performance of our reservoir model to identify the required bottom hole pressure for a certain injection rate that we want to achieve. And on the other side, which is LedaFlow, the same IPR table will be used to determine the rate and pressure to honor our constraint at the wellhead conditions. There are a couple of guidelines that we normally suggest in order to achieve a successful coupling process at the end between LedaFlow and GEM. Before we look at these guidelines, it's useful to have a kind of further details of how the setup will be happening between the LedaFlow and GEM when we want to couple them together. In this right hand side schematic, I am showing the typical GEM model with some grids and a typical LedaFlow wellbore model with some discretized grid block as well. Let's assume we're gonna perforate these two blocks in GEM model, and then with the equivalent length of that perforation zone in GEM, we're gonna define the same length of the inflow zone device in LedaFlow to couple these two applications together. GEM normally produces the IPR table at the reference layer, which is the top most perforated grid block, and when that IPR table in terms of some rates and BHP is generated, that information will be passed to inflow zone device in LedaFlow for further calculations inside the wellbore. Here are some of the guidelines that we normally advise to do. First of all, we suggest to use the number of the data points very carefully in GEM reservoir model to ensure that we are capturing the non-linearity relationship between the BHP and rate. So more non-linearity will require more data points to capture that relationship effectively. We also use the operate max BHP keyword in the GEM dataset because that allows us to scatter the data points effectively over the BHP range in the IPR table. As you can see also from the schematic in here, the place that we are reporting the BHP in these two applications is quite different. LedaFlow will take the BHP position as the center of the perforated zone, while GEM will take the top perforated grid block center to report the BHP. So in certain cases, when we're looking at a very long perforated zone, there would be quite significant difference between these two positions. So we suggest to use the BHP depth keyword to correct the GEM model to the same reference depth as the center of the LedaFlow inflow device.